Alright, so this is going to be section 3.3, and it's about global maxes and mins, or absolute maxes and mins. Okay, so on this graph here, we've seen a graph similar to that before. We have a local max there, we have a local min there, and we have a local max here. Now, those are all local, right, to each other, but when we want to find the global max or min, right, that means you have to take the whole picture into account, right? So where can the global maximum occur in this picture? Well, in this picture, the global maximum was chosen out of our local maxes and mins, right? So we had to look at our local maxes and mins and figure out which local max or min was the biggest. Okay, so in general, the global max came from a local max. Okay. Similarly, we could look at this picture and say, well, is there a global minimum? And it would be hard to determine because our function is just going down. If we assume that this function continues down, we would say that there is no global minimum. However, suppose that I say, well, I'm going to redraw this graph. Oops, that wasn't a very good picture. But now I'm just going to cut off the graph here and here. Oh, let me just redraw a picture. And let's say my picture looks like this now. Okay, so in this case, the global maximum is again one of the local maxes or mins. But now, is the global minimum one of the local minimums? No, in this case, the global minimum actually occurred at an endpoint of the curve, right? And so here the global min didn't occur at a local min, it occurs at an endpoint. Okay, and so we see here basically that when I'm looking for a global max and global min for a function on a closed interval, I have to check two sets of points. One set of points is where we have local extrema, and the other set of points is where we have endpoints. Okay, and so let's summarize that with the following theorem. This is the extreme value theorem. Some people will abbreviate it EVT, the extreme value theorem. If f is continuous on the closed interval from a to b, then f attains a global max and a global min on the interval. Good. That's all we need. We need f to be continuous and we need a closed interval. So this is important, right, that the interval be closed. That means that we include the two endpoints. So for example, suppose that the interval was not closed. You could have a function that looks like this, where x equals 0, for example, is a vertical asymptote. And then, if you open this interval up right here, right, and don't include the point x equals 0, then this function does not have a local max or a global max, for example. Good. So it's really important to include those two endpoints. Excuse me, I've been drinking too much coffee, I guess, or maybe not enough. The other piece is, where can you find, so this is a existence question, right? So we know that if f is continuous on a closed interval, our global maximum exists. Now, where do they occur? That is, when I say they, I'm talking about the global maximum or a global extrema. Well, we have to check critical points and endpoints. And so these are where the maxes or min can occur. So to actually check, you want to build a table, x and y. And so in your x values of your table, you want to put in your critical points and endpoints. And then over here, we just look for the largest and smallest values. And those will be our global max and min. Good. And so this is a really easy way to check for global max and min as long as you have a continuous function on a closed interval, right? Those conditions are really important. Good. So I'm going to pause and set up an example. Good. So we'll be working through activity 3.3.3. Let's take a look at x e to the minus x on the interval from 0 to 3. Okay, so again we need critical points and endpoints. By the way, this function is continuous on the interval because it's just x times the exponential function, right? Both of those functions are continuous, so the product is continuous. Okay, so to find the critical points, we set the derivative equal to 0. And so the derivative is product rule here. Derivative of x is 1 times e to the minus x. And then when I differentiate e to the minus x, the negative sign is going to pop out. So I'm going to go ahead and put the negative sign there. Okay. Good. Now when I set that equal to 0 and solve, I can factor out the e to the minus x here. Good. E to the minus x is never equal to 0. So therefore the only way this is equal to 0 is if x is equal to 1. Good. And now that's the only critical point, right? Because this function is always defined, so there's no place where it doesn't exist. Our x and our y. Let's go ahead and put in our 0 and 3. We'll kind of put these in order, and then a critical point at 1. And now we just plug in each of these points into our function and see which one's the biggest and which one's the smallest. So when you put in x equals 0, you do get 0 there. If I put in x equals 1, I get e to the minus 1 power. And remember what that is? That's about 1/3. That's real rough, but about 1/3. That gives us a good idea. And then what happens when I put in a 3? I get 3 times e to the minus 3. So what is that? That's about 3 divided by 3 cubed. That's really rough. So that's about 1/9, I think, right? Isn't that about 1/9? And you can plug that into your calculator, right? Here's my calculator. Let's see, I need e to the 1 power, so I'm going to hit a 1 button and then the inverse of natural log here, and then flip that over. So this is equal to 0.367, and then 3 times, and then I'll put a parenthesis there, and then let's see, 3 minus, and then the exponent for that, and then put the other parenthesis on there, set that equal. That's 0.149. Okay, so where's our global maximum and global minimum? Our global minimum is 0. In fact, let me just put this here for a second, min, and this is our max. And so let's write down verbally how we would say this, right? So the global minimum for h of x is 0, which occurs at x equals 0. So remember that the minimum itself is the y value. Same thing for the max. The global max for h of x is, well, excuse me, e to the minus 1. which occurs at x equals 1. Good. So at x equals 3 we don't get either. All right, let me clear my throat and I will try another problem. All right, so part B has some trig functions in it, so we haven't done those for... Oh, my Alexa is starting to talk to me. Hang on. Okay, I think she's finished. Okay, section B. P of t equals sine of t plus cosine of t, and our interval is between minus pi over 2 and pi over 2. Good. So we need critical points and endpoints again. We have our endpoints. Critical points are where the derivative is equal to 0. So derivative of sine is cosine. Derivative of cosine is minus the sine. Set that equal to 0. And we have that cosine of t equals the sine of t. Good. Now you could write that as like the tangent equals 1 if you wanted to, but if you look at the unit circle, I think it's pretty straightforward because the x coordinate and the y coordinate are equal. So that means that we're along the line y equals x. And so we have one solution at pi over 4, and then the other solution is over here, but we're only going from minus pi over 2 to pi over 2. So pi over 4 is the only point that we have. Good. So now we can write down our x and y. We start at minus pi over 2, go to pi over 4, and then we have a pi over 2. And then we plug in those to our sine and cosine. Good. So what is the sine of pi over 2? Well, if you forget, you can draw a little sketch here. That's a sine. Here's our cosine. Right? So sine of negative pi over 2 is back here. Right, so this is pi, and so pi over 2 would be right there. So that sine of pi over 2 is negative 1. So at pi over 2, sine is negative 1. Cosine of negative pi over 2 would be 0. Okay, so at negative pi over 2, we'll be adding negative 1 and 0. So we'll have a minus 1. And then what happens at positive pi over 2 while we're sitting here? At positive pi over 2, the sine is 1, but the cosine is still 0. Right, so 1 plus 0 is 1. And then what happens at pi over 4? In that case, sine and cosine are equal. So that's 1 over the square root of 2 plus 1 over the square root of 2. So that's 2 over the square root of 2. Good. How big is that? Let's see. 2 divided by 2 square root. So that's the square root of 2. Square root of 2 times square root of 2. Yes, it is. 1.41. So again we have our global min here at negative 1 and a global max here at pi over 4 max. So again, how do we describe that? We would say, just like up here, the global minimum is negative 1 and appears, or it occurs at x equals negative pi over 2. The global maximum is 1.41 or square root of 2, and it occurs at x equals pi over 4. Good. Done. Okay, maybe we'll try one more example. Okay, I didn't realize I was running this video so late, so let's see what we can do here. So we have q of x is x squared over x minus 2. This is 1c, or activity 3.3.3, number part C. And we're on the interval from 3 to 7, and we want to get the maximum global maximum on the interval. Okay, so I've already started the derivative by using the quotient rule. And so let's go ahead and simplify that. We're trying to find the critical points, right, for our interval. And so if I simplify that, I get, let's see, 2x squared minus 4x minus x squared. And that's on the top, right? And so that's going to be, what is that? X squared minus 4x. And then on the bottom we have the x squared, x minus 2 quantity squared. So q prime of x we see is, I'm going to go ahead and factor that, x times x minus 4 divided by x minus 2 squared. Good. So where are the critical points? Well, we have 1 at 2 because that would make the derivative, or that makes the derivative not exist. But notice that our function also doesn't exist there. And in fact, I believe we have a vertical asymptote at x equals 2. We'll double check that. Okay, and then what happens at, let's see, x equals 0 is going to be the other critical point, and x equals 4, so x equals 0 and x equals 4. Those are points where we're setting the derivative equal to 0. Okay, so that's where the numerator is equal to 0. Good. Yeah, this vertical asymptote is right. Oh, hey, we lucked out. The vertical asymptote is not in our interval, so we don't have to worry about it. Good. Is 0 in our interval? It is not. So 4 is the only point we have to worry about that's in our interval. Okay, so our points are 3, 4, and 7. Okay, and now we just plug those into our q of x over here and see what we get. So with 3, we get a 9 divided by 1. With a 4, we get 16 divided by 2. And with a 7, we get a 49 divided by 5. Good. Let's see, 49 divided by 5, is that bigger than or less than 9? We might want to get a little bit of an approximation there. So grab your calculator. You can grab your calculator for that. And it's 9.8. Good. So it was important to see, right, that that's going to be bigger than your 9. Okay, because now what's our conclusion? We have a global minimum at 8 and a global maximum at 9.8. So we'll say the global max of q of x is 9.8 or 49/5. I guess the book wanted us to get an exact value. It occurs at x equals 7. Okay, and the global min is 8 of q of x is 8, and it occurs at x equals 4. Good. Now remember, this is only true on this interval, right? So the global max and min depends on the interval that you're looking at, because remember at x equals 2 we had this probably had a vertical asymptote. We were lucky that we didn't have to mess with that. And then at x equals 0 something might happen as well, but again we didn't have to mess with that because that was outside of our interval. So the only point that we needed to check was x equals 4. Good. Now I've run this video way over, so I need to stop here. We might try some extra ones. I'll take a look to see what the problems look like.